Hi everyone, and welcome to today's webcast, which looks at AI and deep learning for imaging and machine vision. It's fair to say that these technologies have helped to evolve the way that visual data is processed and analysed. From self-driving cars to medical image analysis, technologies are transforming industries, with many applications having benefited from the opportunities provided. Today's webcast is designed to offer advice from our three expert speakers, including best practices, real-world examples, to help overcome common challenges and unlock the potential of these technologies. My name's Keely and I'll be your moderator today, and I'm delighted to introduce our expert speakers, Rob Webb, Product Sales Specialist at our very lovely sponsor, IDS Imaging Development Systems, Arturo Lopez, Co-CEO at ISR Specular Vision, and Michael Stezel, Founder and General Manager at MST Vision. In terms of our format, we'll have each of the presenters present for 15 minutes or so, and then we'll have a short Q&A or discussion. For the Q&A, feel free to send your questions as they occur to you, and we'll ask them at the end, but you don't need to wait until the end. So without further ado, let's get started. I'll hand over to Rob. Rob, the floor is yours.
Good afternoon, everybody. Thank you for taking the time to join us here today. I'm pleased to talk to you now about building and deploying AI-based machine vision systems. And I'd like to take a couple of minutes to introduce IDS to those who don't know us already. IDS is a leading imaging company and manufacturer of digital industrial cameras. We adapt key future technologies from the consumer world to make them suitable for industrial use. IDS made the USB interface industry compatible for the camera sector. And our latest innovation is the user-friendly AI-based all-in-one vision system, IDS NXT. True to our philosophy, it's so easy. And you can see a few facts about us here to give you a picture of our experience and size. Our headquarters are in Obersalm, Germany, and we have offices around the world with representation in North America, Asia, and further offices around Europe. Very briefly, our products can be divided into three sections. We have our UI 2D cameras, which offer board level and housed cameras with USB and GigE interface options and resolutions up to 45 megapixels. The Insenso range is our offering for 3D applications like logistics and robotic guidance. And finally, our NXT range is our embedded camera series offering AI analysis. With the NXT, we offer the imaging and processing platform with our NXT cameras. And through a cloud-based software platform called Lighthouse, users have a guided and easy-to-use interface for data annotations, model building, and application development. We also have a partnership with a company called Denkvite, offering their learning-based software called DenkNet, and this offers the ability to solve the more complex deep learning applications, but still with an easy-to-use cloud-based interface for training deep learning models. And we'll see some elements of both NXT and DenkNet over the rest of the presentation. Many of the elements of deploying a machine vision solution based on deep learning are the same or similar to those using traditional rules-based processing. However, the data element of deep learning brings new challenges. So today I would like to provide some ideas on how to achieve the best results in deep learning projects. And this is broadly based on the concept known as machine learning operations, or MLOps. MLOps was originally conceived to make a link between data scientists and a deployed system. From a machine vision perspective, the products available on the market somewhat remove the need for the data scientists and some additional tools, and puts the process in the hands of us as machine vision engineers. However, we can still use and benefit from the principles. We start by scoping out the project, then move to the data collection, through to the model building, and then the deployment, and what we can call the monitoring stage or continuous integration. At each stage, we might gain some insight or spot previously unforeseen challenges, which means we might need to change something in an earlier step to improve the system. For example, during the data acquisition stage, if the application is for detecting defects in a product, we might find that we don't see certain defects very often, and it can be challenged to acquire enough data for this to build a reliable model. So this might change the scope of the project, or it could change the timelines. Obviously, we want to mitigate this as much as possible during the designing and scoping stage, but things often come out in later stages that were not considered, so making adjustments on the fly and as early as possible is the best approach. So let's jump into the MLOps method. The first step is designing or scoping out the project. we need to ask, actually first, is it truly an AI or deep learning task? And whilst AI and deep learning is popular and very much a buzz term, we do need to consider whether traditional image processing could still be the best option. So we ask, what do we need to do? What is the task? Do we want to detect something such as defects on a product, count objects that might appear randomly, or locate or identify something, or maybe we want to read challenging characters for an OCR application? The rule of thumb is if it's something that a human would be able to detect by eye and is variable in nature, it's a candidate for deep learning. If we need quantitative measurements, such as measuring the diameter of a can to micron accuracy, this is unlikely to be an AI task and is best served with rules-based algorithms. Once we have defined the task and established that deep learning is a suitable approach, we can define some metrics. And there's lots of things we might want to consider here, but typical requirements would be how many parts per minute or per second do we want to inspect? What is the minimum target quality score for a positive detection of an object? And with respect to reject mechanisms for a manufacturing line, or maybe cutting a safety cutout on a health and safety system, how quickly do we need a result for a system to operate effectively? And then we can use these metrics to guide what we do later on. These metrics then feed into the resources. Here we want to consider the processing methods, where the processing happens, what the hardware platform should be, and how we will interface to a wider system. We can look at benchmark figures to give us some indication of what would be necessary. But with the NXT, we have a known processing target, so we can be specific about the hardware requirements even at this early stage. Having considered the processing hardware, we also need to think about the human resources. Acquiring the images for a deep learning-based system can be time-consuming and should not be overlooked. It might not be a human-intensive task, but it could still take a long time to accrue enough images for the application, so this would need to be planned for. We need to annotate the data. In some cases, this is an entirely manual process, which could take a long time to complete. The good news is that there are ways to accelerate this, and we'll look at some of these later on. Once we have a working system in the lab, we have to consider the time and effort to deploy that system at the end customer. And there's no simple answers to the time involved. This knowledge really only comes with experience, but certainly should not be underestimated. The last section here is a proof of concept, and this can almost be seen as a mini project cycle. First, we're looking to scope out what we want to achieve as part of the proof of concept. The advice is to start simple. So, for example, we might pick just one defect out of 5 to start with. We need to collect some images to work with, and if we don't already have some, and the platform used depends on how many images we need. It could be 50 to 100 images per class or per defect in some cases. Now, this can often be a stumbling block for even the proof of concept phase. Again, I have good news here, since with DECnet we can run a reliable proof of concept with as few as 10 or 15 images per class. We need to annotate the images, and then we need to build a test model in order to test some of the agreed process. Both our NXT solution and DECnet software provides the means to test this without any software development. At this stage, we can gain a good indication of the potential success of the project and the approach, and this is always good to present to stakeholders at an early stage to gain approval for the rest of the project. After we have a successful proof of concept, we can start to work on the main project. The next step in our process is around the data, and this is perhaps the most significant element of the MLOps process. In the past, deep learning-based systems have been very much model-centric. This means we would acquire some images, perhaps without too much consideration, and then work hard on the model to find a working solution, and this required deep learning experts. More recently, there has been a drive towards data-centric AI, where our focus is on acquiring good quality data in order to achieve the best results. The steps we see here are supporting this data-centric approach. So we will achieve better results if we agree a set of rules of how we will acquire the data. For example, what will be in the image? If we consider a person detection application, do we want images of just head and shoulders, or do we need to include full bodies? The application will likely dictate what is required, but it makes sense to be clear on this now rather than end up with data that is half and half and then have to acquire more data later in the process. We also need to consider any variations that will be present in the application and ensure that our training data includes these variations. We can see here a video of the different training images for a Lego gear detector, where we see a variation in brightness and backgrounds in order to deal with the variations that the application will actually see. How many variations you need to deal with will be very much dependent on the application. It could be purely related to product variations, and everything else is fixed and constant. But at the extreme end, there could be an incredible amount of noise in the image. Consider self-driving cars and the sheer variety of things in the scene. The application would be primarily detecting cars, roads and pedestrians, which needs to be present in the data set. But in the scene, there will be signs, buildings, street furniture, trees and bushes, along with the variation that different weather types can introduce. So we need to make sure that is all represented in the data. Once we have set the rules around the images, we can start to collect the image data based on these rules. If it is at all possible, the images should be taken using the same camera and in the same position as the final installation. But this is not always a realistic demand if the system is still to be built. So it may be possible to use existing data at this stage, as we may have done with the proof of concept. But better results will always come from data sets that are entirely representative of the end deployment. Once we have collected our data, the next thing we need to consider is the annotation of the data. One of the key principles here is consistency. If we take the example of our Lego gear detector again, we might define that the bounding boxes are drawn around the gears tight to the edge of the parts. So we'd want to be consistent in how the bounding boxes are drawn to get the best results. And this is of particular importance if we have multiple people annotating the data. We also need to consider how we will deal with occlusions. Again, looking at the gears, we might decide to draw bounding boxes around only the visible area of the gear, or we might decide to draw the bounding box around where we expect the entire gear to be. Either approach is fine, and will likely be dictated by the application. But the key once again is consistency. As a side note, the process of annotating data can be extremely time consuming and also tedious. More and more we are seeing tools that accelerate this process. With DenkNet we have a one-click annotation tool which runs a pre-trained network to gain some idea of how to segment the parts, and then as an annotator we simply just need to click on the item we want to label and the bounding box is automatically applied. This also works with segmentation, where we are looking at pixel accurate annotations, and it's possible to deal with overlapping parts also with an additional click or two. Having experienced manually labeling images, I can say from personal experience that this truly is a massive benefit. For our data, it also really pays to have good organization. We should have consistent labeling of images as well as consistent annotation names. And it's an extremely good idea to include some notes about the data set, who created it, when, what it contains, and any comments. As we're working with an iterative approach in our MLOps model, it's highly likely that we will come back and look at these data sets in a few months' time, maybe even a year, and trying to remember what each data set consisted of is rather challenging. Therefore, any notes we can apply are a useful prompt. Likewise, we want to be sure that our file structure is also well planned and uses good understandable naming conventions if we're storing data locally. We often use data augmentation to increase the number of samples that we train from and build in more synthetic variations. And with this, we just need to be sure that these variations are loosely representative of variations we will actually see in the application rather than things that wouldn't be at all relevant. And the final point here is that we need to ensure that we have a test data set. And this should conform to all of the previous rules and guidelines we have set, and we should ensure that as many of the product or ambient variations are present in the test set. This data set should be kept totally separate from the training data so that when we are testing, we are certain that we are only taking results from new images. So getting the data element right makes the later steps much, much easier. Now, when it comes to building the model, we have only to select the model type and experiment with any models we build. The model selection will largely be determined already during the design stage, whether that's image classification, object detection, segmentation, or some other method. And by keeping this simple and user-friendly, this is more or less the only decision we have to make with our examples, DenkNet and NXT. Both NXT and DenkNet provide a graphical feedback on the training success, so you can see how well the model has trained. DenkNet even provides early candidate models to test with whilst the training continues, and the Quality Center allows the user to dig further into the results. With NXT, we can also see a confusion matrix, which plots annotations against predictions and highlights areas where there may be some issues. And we can also test the processing performance on our hardware platforms by exporting models from the cloud-based environment and test on the target hardware. And then linking back to our iterative MLOps model, anytime we find low performance or issues, we can revert back to the image data and refine any elements here. Once we're happy with the model that we have built and it's running in the lab, we need to think about deploying the system. When it comes to deploying the system, if we haven't already pinned down the processing hardware and interfacing, we of course need to do this and develop any software and test the solution before deploying to site. When we come to deploy the system, there are a number of ways that we might do that. We may deploy a shadow system where our deep learning systems is not making critical decisions, but only accruing results and statistics that can be compared with an existing quality control process. We might also use this opportunity to acquire more images for training purposes, especially to capture images of the more infrequent defects or occurrences. Once the performance is at a sufficient level, we can turn the system on completely or move to another deployment method. Another way to work is the canary method. We might divert 10% of the product or decision process through our new deep learning system until the required performance is proven. If problems are detected and we need to go back to an earlier stage of our MLOps process to refine things, we haven't committed 100% of the products to inspection and accrued a whole load of false defects, or worse, passed lots of defective product. We might also use an A/B deployment method where the existing quality control process or system stays active alongside the new deep learning based system, and we can switch between the two. Again, should problems be identified with the new deep learning system, we can switch back to the original process whilst the issues are addressed. The key thing is that if we are replacing an existing system, we have a fallback plan should the performance not be where we expect. The final piece of our MLOps model is very important as we need to monitor the system over time. We can collect lots of statistics to monitor the general system health, as well as metrics related to the vision side of things. For example, is the average pass score or image brightness that might affect the performance changing? And by monitoring all the elements, we can be alerted to changes in the system, perhaps through data drift, where the image data starts to change for some reason, or concept drift, where there may be a change in the expected or intended results. There are things that can change over time. For example, ingredient or process might change the appearance of organic products, or defects in products may change over time. Also, social or political changes can affect data. Consider the effects of use of face masks during the COVID pandemic on face detection algorithms. Or we may also see seasonal variations in product that may not have been present or available when the system was originally deployed. It's important, therefore, to keep reviewing any deployed system to ensure that external factors are not affecting the performance. Anything detected can be taken back to earlier stages of the MLOps model to refine and improve. So I hope I've been able to illustrate the benefits of the MLOps process, especially the iterative nature of it, that we can really benefit from having this data-centric approach with a strong focus on images, consistency in images and annotations, and a good structure of data. And we can start with small proofs of concept to gain confidence at an early stage and learn some important early lessons. And finally, monitoring the deployed system to identify issues that can be easily corrected. IDS offers deep learning-based products that very much support this methodology, and if you have any applications that you would like to discuss, please contact us via phone, via email or LinkedIn, and we will be very happy to assist. But for now, thank you for your time.
Thanks very much, Rob. That was a really interesting presentation filled with some great content there. Thank you ever so much. I'm now going to hand over to Arturo. Arturo, the floor is yours.
Thank you, Kelly. As our speculative vision is a project born on the idea of taking industrial quality to the next level. So how did we start it? We started as our primitive sector, the automotive, working with light and tier 1 companies on aesthetic quality of parts. Later on, we developed technologies to do the same thing on steel and glass sector, but still today the automotive sector is quite important for us. So in this presentation, we want to give you insights on our main applications and how they are applied in the industry, focusing on automotive and steel markets. From the image acquisition to the machine learning approach, trying to renew the quality control in industry. So how do we do it? We started always by having a part component that needs to be inspected with defects on its surface. So we study the part, the component with the customer in order to fulfill all the requirements given. After that, we focus on the process. The process is given all of the possible requirements regarding cycle time, regarding minimum defect size, regarding the dimensions, and any specific requirements from the customer. And we develop such systems as you see here in the right, in the image in the right, which are slightly different between each other. You see, why are they so different? The topic here is we focus on the image acquisition. So systems are specifically detailed and designed for making the image acquisition first and then doing the processing. So let's see some examples on the industry. First, this is a headlamp system inspection for a tier 1 company. This is right after injection or coating. And here we are looking for defects that are typically coming from these processes, injection or coating. Same concept for real lenses, smaller parts, but with the same goal, to look for defects here located in this kind of edges or flat surfaces, even different colors. They could be amber, they could be red, or even what we see in this example here, they could be black, opaque, with reflective surfaces, and what it is our specialty is transparent areas. So at the end, what we are looking for are these defects, which could be anything, as here you see in the image in the video, with any size, but which are correctly detected and make the automatization of the quality control. But are we really looking for this only? And here it is where the machine learning comes. No, we are not looking just for bubbles or for dots or scratches, flow lines, in this case, in these automotive injection processes. But what we are really looking for is the classification of the defects, grains, dots, anything that we detect. We try to classify them with machine learning algorithms that we develop by making labeling of all of the defects that we have found in this history that we have, that's so long. but this is the result, and this is what is really important for quality control. I'm going to show you some examples on the automotive sector, injection processes, and also in the steel sector. And then after that, in the final slide, we will see where are we going with this technology. So typical defects could be lack of material, scratches, as small as 0.1 even for interior lighting. We'll see in the next slides. This is, for example, how it works in the industry for a complete cycle, looking for the defects and even having possibility to make the cycles divided by results or defects classified. And all examples for applications in this automotive injection sectors are lenses, or as said before, interior lighting, which is quite more complex because of the minimum defect size which is permitted here in the ONS requirements. For example, look at that black dot, that point, quite small. This is why we first focus on the acquisition images, and then we try to process them, and important to classify the defects. So, the steel market or steel sector, what are the differences here? It's about artificial vision again, but it's something totally different. Here, the factory atmosphere and the conditions are not so gentle as in the automotive sector. So in this way, we need to integrate systems in quite rough lines and with conditions that are dirtiness or dust in the atmosphere and so on. Even though we are able to detect defects as small as 100 microns for scale, for example, in these ones. But as you see, the industrial system needs to be quite prepared for the industrialization of the artificial vision system. It's not just the camera that you have to put inside the system. In this case, we are using linear cameras, taking advantage of the movement, the advance of the material in the coil. And these are just some examples of how difficult it is to integrate systems in such conditions here. But at the end, we managed to have quite good images in our software, which helps the customer to detect and classify the defects all over the surfaces of the coil. In order to see them better here, as I kind of zoom in, these are quite small defects located in all over the coil. These are small residual oxide stains, which are of course not permitted by the customers of our customers. Here is how it looks like a software or an interface with more density or concentration of these stains, black stains. And of course, the system is also possible for the system to watch or to detect the macro defects, so bigger defects than 100 micron. So after coming all this way through our applications in these two sectors that we have focused in this webcast, what we are, with the direction that we are taking in this sector or in this machine vision applications, is that the next level of the quality control. That is what I meant before in the beginning, that our idea where we were born is to take the industrial quality to the next level. So this is the point where we want to go. We want to understand the region of the defects, taking into account the quality inspection that we are doing at the end, so in the product, and also having into account the parameters of the process, what defines the process and what makes the defects appear. For this, we are using models with machine learning algorithms, using AI to boost this technology. And our goals are to improve the profit of the processes and reduce the pollution or the carbon footprint present on the processes that we are involved. So the main topic, the main idea is we know what defects we have at the output, so we want to go to the beginning of the process and predict what defects we will have in the future if we keep the same conditions or if we keep the same parameters. This is how we try to reduce or to improve the quality control in our lines where our systems are installed. And this is all driven by the new models of AI and deep learning. So we hope you like it. This is how ISR Specular Vision is renewing the standards of the quality control in the industry. So if anything is unclear in this presentation, or if you want to know more about this technology, just please go to our website or LinkedIn profile, and you can look for information or directly contact us. Thank you for that.
Thanks, Arturo. That was great. It was really, really interesting to see some application examples there. So thank you very much. And now, last but not least, I'm going to hand over to Michael. Michael, over to you.
Thanks, Kili. So let's start sharing the screen. Okay, I should see it now. So thanks for giving me the opportunity to give also my presentation. First, my agenda. So I will, as all of us presenters, I will show a few slides about our company, then technologies we are using in our applications, and we show some real examples of applications we discuss with customers or we do with customers, and just one slide as a conclusion. Coming to our company. So we are a small team close to the city of Frankfurt, so city is Mainz. We consider ourselves as a development service provider. So we help our customers to solve technical problems. Our customers are mainly integrators, system integrators, or in-house engineering departments. In services, we use a powerful tool. Most important tool we're using is MBTEX Helcon, which is also already one of the questions I saw on the question list. So yes, we are using Helcon. So I am able to answer a question immediately in my presentation. We are using Visual Applets, which is a development environment for FPGAs from the company Basler. We provide a lot of feasibility studies. We do trainings. We love line scan cameras. We also train Helcon. We train a guideline which is named 2632 to evaluate the performance of inspection systems. Actually, we are just doing all phases of R&D projects, and we also provide technologies and turnkey solutions. Coming to technologies, I show you the most important ones later in the next slides. Just a few examples. I mentioned Helcon, I mentioned Visual Applets. We do a lot of technology studies, so we do completely open book projects where we discuss which software to use or which technology to use. We do optomechanical integration and complete systems. Coming to most important technologies, because this is also why I present here, because we face a lot of challenges when our customers want to apply deep learning models. Customers come to us because they have some technical issue, and one of the technologies we are selling, we call it multi-channel. It's just time division multiplexing. Other companies call it multi-flash, multi-cycle, multi-exposure. It's just using a line scan camera, and instead of using a bright field, a dark field, a reflective channel, and 3 cameras and 3 frame grabbers, we just use one line scan camera, which needs to be faster than needed, and we strobe through up to 10 different illumination setups, either different angles, different wavelengths, any property of light, using the frame grabber to acquire the mixed data stream and rearrange the data within the frame grabber. So you receive, in this example, 3 images, like the dark field, the reflective channel, and the backlight. And we help our customers to show their defects with a better contrast. Second technology we are using as an add-on to that one, it's photometric stereo. So we do photometric stereo within the FPGA at extremely high bandwidth. For those who don't know photometric stereo, it's also called shape from shading. Actually, you need to take 3, or most of the vendors using 4 images of the same scene with 4 different independent illumination directions. And using the 4 images, you are able to calculate surface properties like topography, but also the reflectivity, which is named albedo. You see the typical application of bright dot print on a pharmaceutical package, and sometimes it's difficult to read the bright dots. Using this technology, you can separate the curvature from the texture, and you see on the left side, it's very easy to see the bright dots. We do this, as mentioned, with line scan cameras at extremely high speeds. The new version is able to cover 3.6 gigabyte a second. And there was no light available, which perfectly fitted our needs. So we developed a new light, which we actually present to the market yesterday on LinkedIn, and we will show it on the Vision Show in 3 weeks. So what does this have to do with this presentation here? I show an example because we always try to work on the image part first. We do image processing, so we focus on the image. We are not allowed to show you the real application, but we created a fake one. So we printed our MST Vision logo flat on paper. We printed the image of insects on the paper, and we added 3 real insects to the paper. In the upper image, it's very difficult to separate the print, the flat print, from the insects. In the lower image, you see using the photometric stereo, it's very easy to see the insects. And that's our strategy we are always using to make the image better, to either using multi-channel or photometric stereo or other technologies from computational imaging algorithms to improve the image quality. Last technology we sell to the market is our high-speed sorting technology. So MST Vision is always focusing, and that's why I'm also talking here, on high bandwidth, low latency applications. And one of the applications we are doing is free-fall sorting, because the problem is you have free-fall granules, and you need to take the decision in millisecond range. If you're too late, the granule is gone, and you can't separate it from the good ones. We do this in extremely high speeds, with extreme bandwidth of 2.5 gigabyte a second, 1 million objects a second, and at a timing accuracy better than 1 millisecond, and also a delay of only 1 millisecond. Now, artificial intelligence. We did this technology a few years ago, just a rule-based classic approach, extremely fast, but we have been limited in flexibility or detection performance or applications. So we had this public funded project and also a PhD thesis we are working on. So we wanted to combine the speed we have using the FPGA with the flexibility and all these nice and cool advantages of deep learning methods. The idea is we do not develop the nets by ourselves. We provide the architecture that our customers can bring their own AI. And we just add, let's say, 1 millisecond to the inference they are using. But now coming to the challenges. A with all the customers, we are facing the challenge that they are not able to meet the required bandwidth, latency, jitter they need for the application, because we are always in high-end business. So we are specializing in the load balancing between FPGA, GPU, and CPU. So for today's presentation, since it's also some kind of training and I teach in university, this is more like an academic slide. At MST Vision, we separate the processing chain into several steps. Again, we focus on image. Image is the most important part in industrial image processing. So we have sophisticated image acquisition technologies, as I mentioned, either multi-channel, and then we can take multispectral images or photometric stereo, which is also named computational imaging. And this we purely do on the FPGA, because we also need to talk about which processing unit, either FPGA, GPU, or CPU, is the best one. Maybe for those who are not familiar with the processing units, CPU is the standard processor you have in your computer. Intel, AMD, so on. GPU is your graphic processing unit. It's your graphic cards in your computer. Most people know NVIDIA. FPGA is not so well known. It's named Field Programmable Gate Array. It's a very small, efficient processing unit, which is available in a lot of electronics, and also on the frame grabbers, which is the electronic card to acquire images with high bandwidth. And the FPGA is extremely efficient. It's there. It's in your frame grabber anyway, so we do a lot with FPGAs. So coming to image acquisition, you acquire the full raw image. In Quark's Express interface, up to almost 5 gigabytes a second, which is a lot. Yeah. And by acquiring more than one image, we even maybe increase the bandwidth. And then we do pre-processing, which you can do on the FPGA. You apply filters, or what we also call smart binning, or some others call it pruning. So we acquire high-resolution images in the frame grabber, and then we reduce the volume using smart binning. Yeah, so of 4 pixels, we put a rank operator and say this pixel wins, or we make an average or whatever. And then the pre-processed data is again still the whole image data, except if you do smart binning, then we can reduce already the bandwidth you need. But now comes the next part. You need to detect something in your raw images. We call it an event. There's something I need to take a decision. You can do detection using classical segmentation, so thresholding and binary large objects analysis. You can use semantic segmentation, anomaly detection. So FPGA can do something, but this is also something where the GPU is really, really strong. So if you use this approach, you know which area you need to take a decision. So instead of the full image data, you only have region of interests, which is Royce mentioned here. And then you need to classify, is this just some type of dust or a noise, or is it a real defect? So you can do this again with classical approach, or most of the time deep learning, which you can do mainly in GPU. And then at the end, you take a decision if your part or area is good or bad, and you need to have some logic in your system to do some interfacing with machines, visualization, logic, state machine, whatever. This is mainly done in the CPU. And you need to decide wisely where and when to use which processing unit, because each processing unit has a lot of advantages and disadvantages. I talk about this at the end of my talk. And you need to consider the time you need to transfer between each of the processing units. And most important in our applications, which unit can process which amount of data, so bandwidth, and which delay and jitter each of these units has. Because CPU is so extremely flexible, but on a Windows system, sometimes you lose many milliseconds. You don't know why. So this is our view on load balancing between FPGA, GPU, and CPU. But now coming to some real-world examples. Yeah, so people in my network allowed me to show some real examples. Let's start with a research project. It's called Serve Code Inspect. It's a big consortium, and overall, they have the aim to enable zero defect manufacturing in flat steel production. So you see, it's a big project, and they want to create better data to know their process, to understand the process, and to correct anything which goes wrong in the production, to have zero defect production. But to do so, they need an inspection system. And they need to inspect coils which are like 20 kilometers long. They are looking for speeds like almost a kilometer a minute. And one coil has like 200,000 events which need to be detected and classified into 50 different classes. Optical resolution is 180 micrometer per pixel. And what they do is, their approach is to have improved detectors, which seems to be something similar to our multi-channel technology. And they want to have better training data to have an improved classification. And they are also facing the same problem: bandwidth, latency, speed. And coming to the second application. So this application, it's just an example where we are not involved. It's just the network. I know the people who gave me the slide. Next slide is from the company we are in discussion with. It's company Strehlen. They have a system to sort nuts. Yeah, the initial system they had was using a hyperspectral camera, and they are also having a second option where they're using RGB line scan camera, and they inspect like 500 millimeters of nuts, have a conveyor speed of 1 meter a second, high resolution. And they're using classic segmentation, using CPU, and then they classify using their own developed deep learning nets. Latency and jitter, and this is a good example on the CPU, and which is not optimized yet, to be honest, but it's still up to 200 milliseconds they are losing on the CPU. So, which is a big problem for them. And then they control the nozzles at a very high accuracy. So this is already well done. And they discuss with us if we can do data reduction by using classical FPGA-based segmentation or using a small CNN to do the segmentation. Then 2 more examples, then I'm done. So lithium-ion battery inspection is one of the applications you see on any show. On any booth, you see everyone tries to go into this market because it's really huge. And this is a company we are in discussion at the moment, IT Gunnar. They showed this on battery show, the system, using a system scan with 500 millimeter, defect size 10 micrometer, which is interesting because the surface roughness is already 30 micrometer. And their approach is using shape from shading, that's how they name it, or photometric stereo, how we name it, on the CPU. So there's one big computer doing just this processing, do the depth calculation, and then using, again, a deep learning approach to detect the defects. And the discussion we have is maybe we use multi-channel to acquire the images and to do the shape from shading calculation within the FPGA, which will hopefully improve the speed a lot. Last example, that's from the company iMation. They are using a so-called contact image sensor for fuel cell inspection. And the calculation was done in the CPU, and then also deep learning was used to find the defects. And we have decided to go for FPGA-based calculation. So we reduce the load on the CPU to give the computer more capacity for the deep learning. And again, the deep learning net is not from us. Customer brings it, and we just help to increase the bandwidth they are able to process. Coming to my last slide, conclusion. When you think about AI is really amazing, yeah, but don't ignore image. Like 4 years ago, there was this tendency in the market, you just use a cheap webcam, the AI can do all you need, which I consider not to be true. Take one or more image with best contrast for each defect you need to detect, like multispectral images, photometric stereo, whatever. Decide wisely regarding your chain of processing, which bandwidth you need, which latency, how much is the cost of your data transfer. And I just added here a small pro and con list. From my point of view, just did it this morning, when to use FPGA, GPU, and CPU. Very short, FPGA is for high bandwidth, low latency. It's very efficient, low power consumption, but it's limited in complexity and special tools and skills are needed for development. GPU is a powerhouse. It can do a lot. It can do complex operations. There are more and more developers and development tools available, but you have a lot of power consumption and still issues with bandwidth and jitter. And the CPU, everyone knows it. It's very flexible. Use it for logic, interfacing. There are a lot of developers and development tools available, but also here, check bandwidth and jitter. And that's all from my side. And thanks for seeing me. And I'm looking forward to the questions.
Thank you, Michael. That was great. Really, really appreciate that. What a good presentation as well there. So we've heard from our three speakers. It's now time to move on to our question and answer session. Please don't worry if we run out of time or if yours doesn't get answered. We do forward them, we log them and forward them on to the speakers afterwards. First question we've had is there any information that AI is already being used in series production in an application? I guess this is for all of you. Rob, do you want to tackle this one first?
Yeah, happy to. Yeah, absolutely. I think yeah, maybe Arturo and Michael are a little bit closer to things themselves, but certainly we have customers using deep learning in applications and in many different production areas. So things like plastic inspection, looking for inclusions and shorts and things like that, through to solar cell inspection, looking for cracks, and certainly looking at food products as well for kind of looking for defective food products. So it's definitely there. We have also a number of customers who are using their own AI with our cameras. If you have a look on our website, we've got a number of application stories there, which cover exactly what's going on. And likewise with our partner, Denkvite, they have some application stories on their website, and these are systems that are deployed and working, and in some cases have been out in the field for a number of years.
Perfect, thank you. Arturo, do you want to take this one next?
Yeah, for sure. Well, AI has been recently improved by all big companies investing on it. So this is why now it could be used. We have the opportunity to use it in industry. Nevertheless, I believe that it still needs time to make it stable, the use of AI in industry, as it is different to use it on servers located all over the world and accessing them through internet, or doing it on the edge. So in the factory, on the devices that are connected or interconnected in the factory. So deploy of models based on AI or machine learning directly online for vision systems, checking quality control or whatever. It's just still, I believe, a topic that needs time to be developed.
Fabulous, thank you. And Michael, could we get your view as well?
Yes. I think AI is evolving a lot. You see it in any booth or any company, or every company is using it. Like all the providers of technologies, as we do, we have applications running in real industry. I'm in the industry since 20 years, so I'm more the classical guy. So sorry for that, because I prefer to know exactly what is happening. But it's amazing to see which applications can be done with deep learning, which I even didn't think which could be possible. Yeah. So I see a clear trend that it will increase the usage and the stability of AI in future. So you can't ignore it. Impossible.
Thank you very much. Thanks. We've got a question come in for Rob. Rob, somebody's asked if it's possible to find out a little bit more about the deep learning model being used, if that was developed in-house or used another network as the basis. Are you okay to take that one?
Depends on which we're talking about. So next to on-camera processing is based on TensorFlow. I think I'm allowed to say that, but yeah. So we're using transfer learning in that instance. DenkNet, on the other hand, is written from the ground up. So that's something that was developed from the university, and Denkvite was a university spin out, and I guess gives us some more possibilities about what we might be able to do on the application front.
Perfect, thank you. And we've had a question for Arturo, and that is, has the technology already been introduced at an industry level or just laboratory concepts? And are you able to make 100% inspection of the parts produced at the injection line or the system?
Well, our systems are now at industry level, so they have been installed in several factories and sectors, not only in Europe, but also in the US. So yes, they are not laboratory concepts. Well, they were maybe 7, 8 years ago, more or less. Now, since 2018, even before, we are delivering them to the factories. And yes, they do 100% of the parts produced. This is the idea. They just come right after the processes where they are being produced, where the defects are created, and then they enter our systems. And yes, the 100% of the part is inspected in these processes.
Excellent, thank you. So we are running out of time now, unfortunately. So that brings us to the end of today's webcast. It will remain on the Imaging and Machine Vision Europe website for the next 12 months, and that's www.imveurope.com. Obviously, please note that the live Q&A won't function on demand. So all that remains is for me to thank Rob, Arturo and Michael. Thank you very much to our sponsor IDS and the Europa Science production team working hard in the background. And last but not least, thanks to everyone who's taken the time to watch this webcast today. Thank you very much. Goodbye.